Okay, let's move to chapter 4. Chapter 4 is about linear transformations. Okay, and starting from section 4.1, we will give you many definitions and examples. Okay, so now let's starting from the definition of a mapping or a linear transformation. So a mapping L from a vector space V into a vector space W is said to be a linear transformation. 线性转换 okay? It's said to be a linear transformation if if we apply alpha v1 plus beta v2, if we apply the mapping to alpha v1 plus beta v2, the result would be equal to alpha lv1 plus beta lv2. That means if we do linear combination first and then do this mapping, the result is equal to we do the mapping first and then work on the linear combination. If the results of these two sequences are the same, we said the mapping L is a linear transformation. Okay? 好 In Chinese, we say that 如果说有一个转换，它拥有这个特性，什么特性呢？就是我先把 V1 跟 V2 先做线性组合，再去做这个转换。如果这个转换的结果等于是我先做转换，再去做线性组合，如果是这样子的话，那我们就说这是一个线性转换。OK， 你先线性组合再转换，等于你先转换再线性组合，那么这样子的转换就叫做线性转换 （linear transformation）。OK， and if L is a linear transformation, mapping from a vector space V into W, we can get this. For example, if we add V1 plus V2 together first, and then we do the mapping, that would be equal to we do the mapping first and then add them together. So in this case, the alpha and the beta is equal to 1. And we now can have vector V. If we multiply vector V by alpha first and then do the mapping, that can be equal to we do the mapping first and then multiply with alpha. So in this case, beta is equal to 0 and V1 is equal to V. So according to the definition mentioned previously, we can get these two properties, right? Okay. And conversely, if L satisfies these two equations, then L, the mapping of alpha v1 plus beta v2, can be written as the mapping of alpha v1 plus the mapping of beta v2. That is equal to alpha lv1 plus beta lv2. Okay. So we can say that L is a linear transformation if and only if L satisfies equation 2 and equation 3. Okay. And if you look at these two equations carefully, you will feel familiar, right? Because, for example, here, this is similar to the concept of closed under scalar multiplication. And this concept is similar to closed under addition. Scalar multiplication, closed under addition. Just as we check the whether a set of whether it's a vector space or not. Remember that in chapter in the beginning of chapter 3, I guess. Right? It's very similar. Okay. So a mapping L from a vector space V into a vector space W will be denoted as this. So L semicolon from V to W. If the vector space V and W are the same, then we said we denote the linear transformation L as V mapping to V. That is referred to the linear operator on V. Okay, and in fact, this kinds of linear operator is what we have done from when we were kids. Okay, when we was in elementary school, just the common addition, multiplication, that is the so-called linear operator on a vector space V. So we will see more example later. Okay, a linear operator is a linear transformation that maps a vector space V into itself. Okay, so just like this, that L be an operator defined by this. So when we input a vector x to do this linear transformation, the result is 3 times x. If we define a transformation like this, okay, for each x in R2. So geometrically, this kind of transformation is looking like this. So originally, the vector x is here. And if we do this transformation, L of x, the result becomes 3x. Okay, the result becomes 3x. Okay, is this transformation linear transformation? So let's check it. Because alpha x, if we input alpha x, then the result would be 3 times alpha x, right? And this is equal to alpha times 3x. And the 3x is actually L of x. Therefore, L alpha x is equal to alpha Lx. Okay? Okay, let's check another property. If we have input x and y, if we add them together, x plus y. So input x plus y, and we do this transformation, it becomes 3 times x plus y, which is equal to 3x plus 3y. That is equal to Lx plus Ly, right? So the mapping L satisfy this property and this property and this property. Therefore, the mapping L is a linear transformation. OK， 好，所以说呢，我们可以定义一个转换。以这个转换来讲，就是我只要丢入一个 input x， 它就帮我吐出3倍的 x。好，那这样子的转换是不是一个线性转换呢？好，那我们就来弄一下。我如果丢入阿尔法倍的 x， 它是不是就会吐出3倍的阿尔法 x？ 那你经过整理之后，你就知道说这个结果呢，就等于是阿尔法倍的 Lx。好，同样的，我如果丢进去 x 加 y， 我是不是会吐出3倍的 x 加 y？ 那经过整理之后呢，我就知道它等于 Lx 加上 Ly。好，那如同刚刚前面这一页所说的，你只要符合这个特性跟这个特性，就等于是符合了这个特性，所以也就证明了这个 mapping L 是一个线性的 transformation， 对不对？它是一个线性转换。好 ，OK。Example 2. Consider the mapping L defined by Lx is equal to x1 e1. Okay, for each x in two-dimensional space. Okay, so now we have a very special mapping L. Given any two-dimensional vectors as the input, the result would be x1, e1. Okay? So, if x is equal to s1, x2, then Lx is x1, e1. That is x1 times 1, 0, which is x1, 0. Right? Okay. So now let's check if we input alpha x plus beta y, that is equal to alpha times s1, s2 plus beta times y1, y2. And then if we add them together, we have alpha x1 plus beta y1 and alpha x2 plus beta y2. If we work on list mapping, as we say here, when we work on list mapping, the result would be we just remain the first item, alpha x1 plus beta y1, and the second item becomes 0, right? Because of here, right? Okay, so this result can be rewritten as alpha x1 0 plus beta y1 0. That is equal to alpha times x1 0 plus beta y1 0, which is alpha Lx plus beta Ly. Therefore, we prove that we do the linear combination first and then do the mapping. The result is equal to we do the mapping and then do the linear combination. Therefore, the mapping L is a linear transformation. Okay? Right? Okay. Geometrically, what does that mean? Okay, because right now, when you input any two-dimensional vector, this mapping just take the first item, right? The result will be looking like this. It remain the first item, and then the second item, x2, will be truncate to 0, right? And geometrically, it's like looking like this. Originally, the vector x is like this. And when we do the mapping L, the L mapping let you project the vector x onto the first axis, right? The geometrical meaning of this mapping is this, x1, e1. So the result is looking like this. OK， 好，所以说这个线性转换的意义是什么？它的物理意义或它的几何意义是什么？它其实做的事情就是帮你把一个二维的向量都投影到，或者应该这样讲，你把这个我们先不要讲投影了，投影是以后要讲的事情。它其实是我把一个二维的向量，我只取我的第一维的分量的意思。这个 mapping 在做这件事，而它是一个线性转换。OK， 好，那在之前的那个 mapping 的意义是，我把原本的向量沿着同样的方向变成原本的长度，变成原本的3倍。好，所以你可以想象得到，其实这些所谓的 mapping， 它可以做的事情越来越丰富哦。除了把向量变长之外，你现在呢可以只取其中一个维度的分量出来。Okay? Example number 3. Let L be the operator defined by Lx is equal to x1 negative x2 by giving any two-dimensional vector. Okay? So, if x is equal to s1, s2, y is equal to y1, y2, let's check if we input alpha x plus beta y, then it becomes alpha x1 x2 beta y1 y2. We do the linear combination first, then we get alpha x1 plus beta y1, alpha x2 plus beta y2. When we do the mapping, so what does this mapping do? We change the sign of the second item. So the first item is still alpha x1 plus beta y1. But the second item becomes negative alpha x2 plus beta y2. Right? And then we do some rewritten. Alpha x1 negative alpha x2 plus beta y1 negative beta y2. That can be rewritten as alpha x1 negative x2 and so on. That is also equal to alpha lx plus beta ly. Okay, so now again we prove that we do linear combination first and do the mapping. It's the same as we do the mapping first and then do the linear combination. Therefore, L is a linear transformation. And in this case, why do we say it's a linear operator? Because originally the input is two-dimensional and the output is still two-dimensional, right? The output is still two-dimensional. The dimensionality of the original, no, as I say, the space, the input space is equal to the output space. So we said this mapping is an operator. It's an operator. Okay. So what is the geometrical meaning of this mapping? Okay. So originally the input vector x is here, and the mapping L would be x negative x2. Right. So the geometrical meaning is that we do the refraction, okay, along the x1 axis. Okay, so this is the geometrical meaning. 好，所以概念上在几何上，这个 mapping 在做什么事情呢？就是你把这个向量以 S1 为轴心去做一个映射，转变到这里来。OK， 好，所以呢，你看这个动作又比刚刚的更为丰富了。我不是只取某一个基底的分量而已，好，我是做一个映射。OK， 好。Example number 4. Another operator defined as if we input x1, x2, the output is negative x2, x1. Okay, is this a linear transformation? So let's verify it again. Alpha s1 plus beta y1, alpha s2 plus beta y2. And right now, the first item becomes negative alpha s2 plus beta y2. The second item becomes alpha s1 plus beta y1. Right? Then we do some rewritten. And again, we found that it equals to alpha lx plus beta ly. Therefore, L is a linear transformation again. Right? And the geometrical meaning here is also very interesting. That means we do counterclockwise 90 degrees. So originally the vector x is looking like this. And then if we do this mapping, we do counterclockwise rotation for 90 degrees. It becomes negative x2, x1. OK， 好，所以这个 mapping 相当于我做一个逆时钟的旋转，我把这个向量做一个逆时钟的旋转，旋转90度。 OK， 所以我们现在呢知道说，这些所谓的线性转换，我可以做什么映射，我可以做投影，我可以做旋转。OK， 好。
老师，
是。
你的投影还卡在那个 example 2，卡了5分钟以上。然后我们从 example 3开始就没有看到。
OK。
好，现在好了，谢谢老师。
OK。Example 3. Let me 网络那么差。好，那我用中文很快再讲一遍。好 ，Example 3在讲的意思就是，我们现在这个 mapping 呢定义成 x1 negative x2，我只要输入 s1 s2，它就吐出 x1 负 x2。好，那它是不是一个线性转换呢？好，经过这一番推导，它是好，因为呢，你只要符合这个特性的，那它就是一个线性转换。好，那这个线性转换实际的几何意义是什么？就相当于是，我以 S1 为轴心，我做一个映射的意思。好，另外一个例子，我如果输入 S1 S2，我做这个转换呢，我得到的结果等于是负 x2 x1。好，那经过这一番推导呢，又证明了它又是一个线性转换。OK， 好，那它几何意义是什么意义呢？如果画个图，它其实代表的意义比较像是逆时钟的转90度。好，我输入这个 S1 S2，我做的这个转换，相当于是我对这个向量我做逆时钟转90度，得到负 x2 跟 s1 这样。OK， OK。So now all the examples we see, these transformations are all linear transformation. Okay, so let's see some other example. Assume the mapping L is a mapping from R2 to R1. What does that mean? That means the input are two-dimensional vectors, and the output is only one dimension. Okay, so we write down a mapping like this, R2 to R1. That is different from this example. For example, here the input is two-dimensional vector. The output is also two-dimensional vector, right? Okay, so in example number 5, this mapping is defined like this. If we input two-dimensional vector s1, x2, the result becomes s1 plus s2. And we know that s1 plus s2 is a real number. It's just a number, not a two-dimensional vector, right? Okay. So let's check if this is a linear transformation. So now, again, we input alpha x plus beta y. And then we transform alpha x1 plus beta y1, alpha x2 plus beta y2. We transform this two-dimensional vector into alpha x1 plus beta y1 plus alpha x2 plus beta y2. And then we do some rearrangement. Alpha multiply x1 plus x2 plus beta times y1 plus y2. And luckily, s1 plus s2 is equal to L1. y1 plus y2 is equal to Ly. So again, this mapping from R2 to R1 is also a linear transformation. Right? Okay? Very interesting. So can you receive this right now? Is there any lag right now? Okay. 有同学在问说简报有没有放在 Moodle 上，第4章还没有啦，还没有。好 ，OK， so let's see some other example. So all the mappings we see right now are linear transformation. So you may think that, okay, so everyone is a linear transformation. No, not exactly. So consider this mapping. So assume we have a mapping M defined like this. Okay, if we input x1, x2, the output becomes s1 squared plus s2 squared and take the square root. Okay, so this is a very special mapping. Okay, in this case, if we input alpha x, okay, the result becomes alpha x squared plus alpha x2 squared and then take square root. And the result is equal to the absolute value of alpha times s1 squared plus s2 squared, the square root of s1 squared plus s2 squared. That is equal to the absolute value of alpha times mx. However, alpha mx should be equal to alpha times square root of s1 squared plus s2 squared. These two are not equal to each other. Okay, whenever alpha is smaller than 0 and the x is not equal to 0 vector, therefore M, the mapping M, is not a linear transformation. So not every transformation is a linear transformation. So this is a special example. Okay? Can you understand this part? Because here, if you write down, expand this part, that would be alpha square s1 square plus alpha square s2 square. That would be alpha square s1 square plus s2 square, right? And then you take square root, right? And alpha square, if you take the square root, that would be alpha's absolute value of alpha. And then s1 square plus s2 square, square root. OK， 好，这边啊，你如果把它展开来是长这样，阿尔法平方乘上 s1 平方加上 s2 平方，开根号嘛。好，然后呢，你这里你看到阿尔法平方开根号，不要冲动哦，你不要想说阿尔法平方开根号啊，就是阿尔法，事实上是阿尔法的绝对值。好，这件事情你以前在数学应该有学过。好，为什么要写阿尔法的绝对值，而不是直接写一个阿尔法呢？因为你今天如果你今天阿尔法小于0的话，就好像说阿尔法如果等于-2好了，-2的平方，好，-2的平方的 square root， 事实上是等于，因为4的正4，应该这样讲，我想一下应该怎么讲。因为你不知道阿尔法是正还是负的啦，好，那所以说呢，当你把这个阿尔法的平方你开根号的时候，你开根号的，因为你平方之后开根号，以前你应该学过说，如果阿尔法是大于0，那么你阿尔法的平方的开根号就会等于是阿尔法，如果你阿尔法是小于0，你阿尔法平方的开根号就会是等于负阿尔法，就好像说你如果阿尔法是-2，你-2的平方开根号等于2，2其实就等于负的-2的那种意思。OK， 好， 所以说呢，这边这里是要写阿尔法的绝对值，而不是直接写一个阿尔法。好，那这件事情呢，其实在好几个数学课里面都曾经出现过，比如说未来在工程数学里面也会有这样子的一个东西啊，就记得，或者在是不是微积分还是哪里，好，就是会有一个这样子的一个要注意，如果你是把它写成是变数的形式的话，好，OK。So let's see some other example. If there is a mapping L from R2 to R3, okay, that means if the input is a two-dimensional vector, we can map it into a three-dimensional vector. For example, here, input is S1 and X2. If the result would be S2, S1, and S1 plus S2. So this mapping defines a mapping from R2 to R3. Okay, so let's check if it satisfies the property of linear transformation. So L alpha x, that would be alpha. The input would be alpha x1, alpha x2, and the result would be alpha x2, alpha x1, alpha x1 plus alpha x2. We take the alpha out, and it becomes alpha times Lx. If we input x plus y, and then we get the result would be x2 plus y2, s1 plus y1, s1 plus y1 plus s2 plus y2, and we do some rearrangement, and then we get Lx plus Ly. Okay, so this strange mapping is actually a linear transformation because it satisfies both this one and this one property. Okay, so this mapping is a mapping from lower dimension to higher dimension. Okay, so if you have heard about a machine learning technique called support vector machine, then mapping from lower dimensional feature to higher dimensional feature is one of the key concept of SVM. Okay, support vector machine. 好，如果你听过一个机器学习的方法叫做 SVM 支持向量机的话，好，你把一个低维度的向量 mapping 到高维度，事实上就是 SVM 的一个核心概念之一啊。好 ，OK。So now, if we define the matrix we define a matrix A by this 0, 1, 1, 1, 0, 1, and if we multiply x1, x2, pre-multiply s1, s2 with this matrix, if we do this, we can get x2, x1, and s1 plus s2. So that we know that how can we do this kinds of projection, this kinds of mapping? In fact, we can use matrix multiplication to implement this mapping. Right? So here, in fact, we cannot write, we should write it like this. A times x for each x in two-dimensional space. Okay? So if you are sensitive enough, you can quickly catch, okay, in this session 4.1, we are talking about linear transformation. So what is the relationship between linear transformation and the linear system we mentioned above in previous chapters? Here is the start. How can we implement a mapping? In fact, we can pre-multiply the vector x by a matrix A. Okay? If you are sensitive enough, you can catch the idea. Right? 好，所以说呢，这边我们又开始在前面 前面10几页投影片，我们都是在讲说，什么叫做 linear transformation， 它有什么特性。好，那这里就告诉你，慢慢的引出说，其实啊，我们刚刚前面讲了好几个有趣的 linear transformation， 映射也好，投影也好，旋转也好，然后这里呢，甚至你把2维的向量转成3维的向量，这些东西可以表达成矩阵相乘。好，所以说呢，这里应该写成这样 ：L of x，L of x can be equal to ax。好 ，the mapping can be implemented as matrix multiplication. Okay, so this is our old friend, right? We have seen a times x all the time in previous 3 chapters. Okay? So in general, if A is any n by n matrix, we can define a linear transformation LA from Rn to Rm. From Rn to Rm by this, because LA of x is equal to A times x. Remember that again. A is a n by n matrix, where the x should be n-dimensional, so that you can do these kinds of matrix multiplication, and the result would be m-dimensional. Ax equals to b, right? Okay, so it transforms an n-dimensional vector x into an m-dimensional vector b. LA of x is equal to A times x, where each x is in Rn. Okay? And the transformation LA is linear since LA of alpha x plus beta y can be implemented by A times alpha x plus beta y. And you can multiply A separately, alpha ax plus beta ay. That is equal to alpha LAX plus beta LAY. Right? So we can think of each n by n matrix as defining a linear transformation from Rn to Rm. Wow. So the functionality of a matrix is rich, is huge, right? It can use to represent a linear system. It can also represent a linear transformation. Okay. If L is a linear transformation, mapping a vector space V into a vector space W, then we have the following properties. Okay. So if we map the 0 vector in the vector space V, then the result would be also 0 vector in the vector space W. So this is the first property. The second property, if we do linear combination of V1, V2 to Vn, where V1, V2 to Vn are in the vector space V, we add them together and then do the mapping is equal to, we do the mapping first and then add them together. Okay. And if we take the negative V, we do the mapping, which is equal to, we do the mapping first and then take negative. Okay. And actually this part is quite simple because this is just, we can set the alpha equal to -1 and we just input the alpha V to do the mapping, which is equal to alpha LV. So you can easily prove the third property. So let's see one more example. Okay. If V is any vector space, then we define a very special operator, or we define a very special transformation that is called identity operator. Okay, that means input the vector V. When we do the identity operator, the result is equal to the input for all V in the vector space. And this is called the identity operator. Okay? And the identity operator, you can easily prove it is also a linear transformation that maps V into itself. And the role of identity operator is just like the 乘法基本元素 ，OK， 好，所以任何的数字乘以一就等于自己嘛，好，那任何的向量，任何的元素，你去做 identity operator 就等于自己，就等于自己 ，OK，OK， so I think this would be a unit, a part of the session 4.1. Okay, any question about this? This is about the end of today's class. 有没有什么问题？之后大家可以注意一下，就是说，我们会把这个，当然会把第4章的投影片放在 Moodle 上，然后会公布对应今天小考的作业啊。那我会请大家下个礼拜要交，好，那就是用上传的方式上传到 Moodle。好，那 bonus homework 的话呢，我可能请助教公告一下，看是可能大家会不会有人不方便来系馆，或者是说可能用上传或者是 email 寄的方式。好，我再请助教研议一下这个 bonus homework。OK， 好，有没有什么问题？bonus homework 呢，大家不见得一定要交，好，你有兴趣你就写，然后你就交，好，那我们今天会公告的 homework 呢，就是每个人都要交，好，就是每个人要交，因为它就对应到小考嘛，好，好，那我们今天上到这边哦。